All right. Hello, class. Good afternoon. Mr. P here. Um, here with another E&M free response. We'll try to keep it to under half an hour like yesterday. I don't know if I showed you guys this mug yet. This is the perfect mug for me. It's got a black Boston Terrier on one side and a brown Boston Terrier on the other. Hey, Mina. I'm super psyched because yesterday I purchased a forge. And because I've been watching this show Forged in Fire for like 4 years now probably. And I keep thinking like, man, I wish I could do that. It looks so cool because they make knives and they make tools using forging. And gosh, it looks cool. And so got my stimulus check and I said, you know what? I'm going to stimulate the economy. And I got a forge yesterday. So I don't know. 3 people voted no that I should not buy the forge yesterday, but I bought it. I thought I was going to stimulate the American economy, but it turns out that this forge is made in Lithuania. So I'll be stimulating the Lithuanian economy, which might be suffering due to COVID-19. Alex, what do I think I'm going to forge first? Probably I'm going to forge a unrecognizable lump of metal because I'm assuming that the first time I try it, it's going to fail miserably. But I'm going to try to forge knives. So that's. I just think I've been wanting to be more handy. I'm a very theoretical person, and I want to be more handy. So this is the first step in that direction. All right. Also, hello to Rowan. Thanks for watching. So let's get into the physics. So this is the 2007 free response. I have not seen this before, so we'll see how it goes. It says, so the first one it looks like is an RC circuit. Student sets up a circuit above in the lab. The values of the resistance and capacitance are shown, but the constant voltage epsilon delivered by the battery is unknown. At time t equals 0, the capacitor is uncharged and the student closes the switch. The current as a function of time is measured using a computer system. And the following graph is obtained. Using the data above, calculate the battery voltage epsilon. Okay. So one of the things I notice is that so this is 1A. One of the things I notice is that the current at time 0 is, looks like it's about 2.25 milliamps. Okay? Now that means that the voltage across the resistor at time 0 is going to be I times R. So it's going to be 2.25 milliamps times the value of the resistance. Let me look up the value of the resistance, 550 ohms. So I'm going to write that as 0.55 kilo ohms. And the reason I wrote it like that is because a kilo times a nano, or a kilo times a milli. A kilo is 10 to the plus 3, a milli is 10 to the minus 3. So those will just cancel each other out, and we get 2.25 times 0.55, which is 1.24 volts. That's the voltage across the resistor. All right. If we look at the capacitor the voltage across the capacitor at time 0 is 0. Why do I say that? Because Q equals CV, and the capacitor starts out uncharged. So it has no charge, which means it has no voltage. That means that the EMF of the battery, according to Kirchhoff's voltage law, the EMF of the battery is going to be equal to the voltage across the resistor plus the voltage across the capacitor, which would be 1.24. All right? Let me see if I have any questions on that. No questions. Cool. Calculate. So B says calculate the voltage across the capacitor at time 4 seconds. So I can see that the current for 4 seconds is roughly 0.4 milliamps. Okay? So that means that the voltage across the resistor at 4 seconds is going to be 0.4 milliamps times 0.55 kilo ohms. So the voltage across the resistor at 4 seconds is 0.22 volts. Now, if we do a KVL loop in this circuit, we're going to have that the voltage across the capacitor is the voltage of the battery minus the voltage of the resistor. Okay? And we just calculated the voltage of the battery as 1.24. So 1.24 minus 0.22 equals roughly 1 volt. Part C. Calculate the charge on the capacitor at 4 seconds. Oh my gosh, that's so simple. Q equals CV. I know the voltage of the capacitor is 1 volt, and the capacitance is 4,000 microfarads. So that's going to give me 4,000 microcoulombs is the charge. All right? Piece of cake. D on the graph, on the axes below, sketch a graph of the charge on the capacitor as a function of time. Charge as a function of time. This is a capacitor that is not discharging. It's a capacitor that's being charged. So what we're going to see is, eventually, once the capacitor is fully charged, it's going to block off the circuit. So the current is going to go to 0, all right, when it's fully charged. So what we'll see is that the charge on the capacitor rises, 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 and it's going to plateau when the capacitor is fully charged. So it'll look something like that. All right. E. Calculate the power being dissipated as heat in the resistor at 4 seconds. Power is I squared R. So that would be, we found that the current is 0.4 milliamps. So 0.4 times 10 to the minus 3 squared is the current. And then R is 550 ohms. Which is about 8.8 times 10 to the minus 5 watts. F says the capacitor is now discharged. Its dielectric of constant kappa equals 1 is replaced by a dielectric of constant K equals 3. The procedure is repeated. Is the amount of charge on one plate of the capacitor greater than or less than? Okay, so, or the same. So what I would say is Q equals CV. Now, as the capacitor charges, the current will eventually become 0 once it's fully charged. Okay? And so once it's fully charged, the voltage across the capacitor is going to be the same as the voltage of the battery. So in both cases, no matter what the capacitance is, the voltage after a long time is going to be the voltage of the battery. It's going to be the 1.24. Okay? So really, the amount of charge is determined by the capacitance. If we put a dielectric with a greater permittivity in, then that increases the capacitance. So I would say that the charge will go up. Boom! That was a long question. I didn't like that one. Question 2. Let me check and see if anyone has asked anything. All right. Man, it's kind of warm today, isn't it? Oh, I just see that and I'm thinking, Gauss's law, here we come. Right? In the figure above, a non-conducting solid sphere of radius A, with charge Q uniformly distributed throughout its volume, is concentric with a non-conducting spherical shell of the inner radius 2A and outer radius 3A that has a charge minus Q uniformly distributed throughout its volume. Express all answers in terms of... Okay. So, yeah, this one's going to be a doozy. So yesterday's free response, piece of cake, I thought. This one, it's going to require some work. This problem, it's not really difficult, but it's very tedious. This is a very tedious free response. So I'm going to get to it. Okay, so I'm going to do a couple of them, the ones that are... so let me just write Gauss's law, first of all. Gauss's law says that the integral of E dot dA is charge enclosed by the Gaussian surface over epsilon naught. Now, this problem has spherical symmetry, so the E dot dA is just going to be E times 4 pi r squared. All right? So really, the difficulty of this is in figuring out what is the charge enclosed, okay, as a function of r. Okay. So what that means is that E equals charge enclosed as a function of r divided by 4 pi epsilon naught r squared. Okay? Now, let's start with the first one. So within the solid sphere, we have the charge density is Q over 4/3 pi a cubed. All right. And if we multiply the charge density times the volume of the Gaussian surface, that would give us the charge enclosed. Okay. So that would be Q over 4/3 pi a cubed times 4/3 pi r cubed. So we can get that the charge enclosed is Q times big R or little r cubed over a cubed. All right. So we're going to plug that into here. and we get that the electric field is QR over 4 pi epsilon naught A cubed. Awesome. Let me see if I have any questions about that. All right. So now we're getting to the second region. And in the second region, if we make the Gaussian sphere bigger in the second region, it doesn't increase the amount of charge enclosed because we're not, by making the Gaussian sphere bigger, it's kind of like, right, if, let's say this is the Gaussian sphere, and you can see that as I make the Gaussian sphere bigger, you get to see more of my face through the Gaussian sphere. But once the Gaussian sphere encloses my entire head, I make it any bigger, it doesn't enclose any more charge, right? Or any more face in this case. So the charge enclosed in this case is just all the charge in the inner sphere, which is Q. All right? So plugging that into this, we get that the electric field is Q over 4 pi epsilon naught r squared. Boom. Part 3. This is the one that's the doozy. All right, so we know that the total charge is Q, minus Q. And the what's the volume of that weird shape, though? The volume of the weird shape is going to be 4/3 pi outer radius minus 4/3 pi inner radius. Okay? Which is 2a. So this is the charge density. 9, okay? And if we take, this one's just a doozy, I think. If we take the charge density and we multiply it by the volume, we would get the charge enclosed. I'll be honest with you, unless you're a geometry whiz, I would just skip this part of the problem. You know, if you get a problem like this when you take the actual AP exam, I would just bail on part 3. I mean, I wouldn't, but you know, unless you really knew what you were doing and you could do it fast, I would skip it. This is the kind of problem where it's just like, it's just laborious. It's warm. I don't even want to do this problem right now, but I will for you guys. So the volume of the outer shell that is enclosed is going to be 4/3 pi r cubed minus 4/3 pi times 2a cubed. Okay, so we multiply that by this, and we get the charge enclosed as a function of r is going to be minus q times r cubed minus 8a cubed over, it looks like, let's see, 9 minus 4. So that's going to be 5a cubed. All right. I think I did that right. Oh no, that's 27 minus 8. So that's going to be 19a cubed. My bad. All right, which you would then plug into this, and you would get the correct answer. I'm not even going to worry about it. Then, outside the spherical shell. Well, if we enclose, we can see that the inner sphere has a charge of plus q, and the outer shell has a charge of minus q. So the net charge of both of those is 0. So if we have a Gaussian surface that encloses both of those, the charge enclosed is 0, which means that the electric field is 0. So that one is the gimme out of those 4. I would say 2 and 4 were really simple, but the other ones were. This one, part 1, or part I, is standard. That is a question that physics students have gotten since the beginning of time. Part 3 is the doozy. All right, this is a 2-pager. Oh my gosh. So now we're on to part B. What is the electric potential at the outer surface of the spherical shell? Explain your reasoning. I would say that the potential is 0. Because what is the electric field outside? It's 0. All right? And if you have no electric field, then when you do the integral of electric field dx, you get 0. All right? So I would just say 0. By the way, this is the definition of potential difference, right? It's minus the integral of E dx. So if you have no electric field outside, that means that the potential at the surface is the same as the potential at infinity, which is 0. Part C. Derive an expression for the potential difference between points x and y shown in the figure. So we know that between points x and y, we have the electric field is k q over r squared. All right? Between the two. That means that the electric potential between the two is given by kq over r, because that's the definition of potential for a single point charge. All right? And so point x is going to have a potential of kq over a, and point y is going to have a potential of kq over 2a. So if we subtract those, what does it want? Vx minus vy, or it wants Vx minus Vy. So I subtract those and I get kq over 2a is Vx minus Vy. Laborious. Oh, look, it's a railgun. See, you've been doing this long enough, and you just see the picture, and you're just like, I know what it's going to ask. Okay? I just see this, and I think, railgun, next. Oh, let me see. Okay. So, in the diagram above, a nichrome wire of resistance per length lambda is bent at points P and Q to form horizontal conducting rails that are a distance L apart. The wire is placed within a uniform magnetic field of magnitude B pointing into the page. Conducting rod of negligible resistance, which was aligned with end PQ at time t0, slides to the right with constant speed v and negligible friction. Express all algebraic answers in terms of blah, 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 blah. Indicate the direction of the induced current in the circuit. So this is Faraday's law of induction. We are increasing the flux because as the thing moves to the right, we're increasing the amount of area, so we're increasing the amount of flux. So we're getting more and more into the page flux. So what does Faraday's law of induction say to that? It says if you're making more flux into the page, I don't like that. So I'm going to create my own flux out of the page. And so that means that we're going to get a current such that it produces its own magnetic field out of the page, which would be a counterclockwise current. Okay. I wonder how many people are watching me still after problem 2. Yeah, there's like no one watching anymore. It's hilarious. Okay, B says derive an expression for the magnitude of the induced current as a function of time. All right, this is kind of interesting, I think. So, so what is? So the first thing I'm going to do is I'm going to figure out that the flux is B times the area, which is going to be L times X, where X is the position of the rail. Okay. Then Faraday's law of induction says that the induced EMF is the magnitude of the induced EMF is the derivative of this with respect to time. The only thing that's changing is X, so it's just going to be BLV is the induced EMF. Okay? If we look at the resistance of the circuit, as the thing moves to the, as the rail moves to the right, the length of wire is going to increase, which means that the resistance is going to go up. So, what is the length of the wire? It's going to be, or what is the resistance? It's going to be lambda times the total length, which would be L plus 2x. All right? Because you have the top part of the wire and the bottom part of the wire. So that means that there is, and then x as a function of t is just vt because it is a moving at a constant velocity. So we have lambda equals, or resistance equals lambda times L plus 2vt. Then we got to divide those two to get the current. Current is voltage divided by resistance. Boom. Derive an expression for the magnitude of the magnetic force on the rod as a function of time. The magnetic force is ILB. And I'm not going to include the sine theta term because the angle between the wire and the magnetic field is 90 degrees. So I have my current there. And so what we get is B squared L squared V over lambda times the quantity L plus 2VT. Boom. All right. Man, this part D. On the axes below, sketch a graph of the external force as a function of time that must be applied on the rod to keep it moving at a constant speed while in the field. So notice that because the acceleration of the rod is 0, the external force would have to just balance the magnetic force. Okay. So really it's just asking for the magnetic force as a function of time. And we can see we have when time equals 0, we just have a certain value for the force. And time is in the denominator, so as time goes on, we have this 1 over x type decay. So it's going to just do one of these things. Or force versus time, like that. D, or E, excuse me. The force pulling on the rod is now removed. Indicate whether the speed of the rod increases, decreases, or remains the same. So if we remove the force pulling the rod, then we're still going to have that magnetic force, which is trying to reduce the change in flux. Okay? So the magnetic force is going to be pointing to the left. So we remove the, so the rod is going to the right. We remove the force that's pulling it to the right. It still has the force to the left. So we're going to find that it slows down. It's going to decrease. All right, let's see how many people made it to the end of the exam. 7 people. You are 7 hardcore students. I applaud you if you made it. State your name if you made it to the end in the live chat. I want to know who made it to the end. I'm going to wait. That wasn't bad. We did this AP exam in 31 minutes. Once again, 31 minutes. I'm waiting. Type your name in the live chat if you're watching. I want to know who are the 7. I'm going to give you a gold star. Wahlberg, Hoon, Christian, Mina, Cody, and maybe 2 people who are AFK. No one else. 2 people who are AFK. I bet that's Rourke is one of the people, and because he's probably just like recording it or something. And then who knows who is the? Maybe I'm one of the concurrent viewers. I don't know. All right. So thank you to the 5 of you who are watching, and I hope you guys have a great afternoon. Bye now.